Okay, so let me remind you quickly what Hugo introduced yesterday. So he spoke about the Ising and Potts models, but I will not talk about that too much. And he introduced the random cluster model. Is that big enough, or should I write bigger? It's okay. So the model was defined in a general graph, but just to fix the ideas, we had a finite box contained in Z2. So this is a finite box here. This is the intersection with the square lattice. And the probability of a given configuration, so a configuration is a subgraph. You declare each bond to be open or closed. And the probability of a given configuration was given by some parameter p to the number of open bonds times 1 minus p to the number of, I will have trouble already, to the number of closed bonds of omega times some topological factor here, q to the number of connected components of omega. And to make that a probability measure, we have to divide by a partition function which depends on p, q, and the domain lambda. So this was the definition, and just to make things a little bit easier for me today, let me introduce another parameterization of this. I will let y be equal to p over 1 minus p. And if you rewrite this, well, you will find out that up to a change in the definition of the partition function, this is proportional all the time to y to the power number of open edges times q to the number of connected components. Again, divided by some partition function. So this is the definition of the model, and there is a link between this and the Potts model. So if we understand the phase transitions of the random cluster model, we will know all we need to know about the real models which have a physical sense, which are the Potts model and spin models on a lattice. So the aim is to prove that there is a phase transition for the random cluster model, and to find what PC is in terms of the value of Q. So finding the exact value of PC is not, in itself, is not so interesting to know the exact value, but to understand why there is a phase transition and how it occurs, that's the really physically relevant thing. So the first thing I want to talk about today is what Hugo didn't have time to explain yesterday. It's called duality. So maybe I shouldn't write lower than this. So duality is something that will help us predict what the value of the critical point has to be. And then I will argue that it's not quite enough, and the rest of today and tomorrow, and maybe the fourth course as well, will consist in proving that actually this prediction that I will do today is actually correct for the critical point. So what is duality? First of all, it's a notion of graph theory. So if you have a graph which is a planar graph, so this is a planar graph. So G, it has a certain number of vertices and a certain number of bonds. So it's a graph, and I'm assuming it's planar. So it's drawn on the plane, and the dual graph G star, which I will draw in red here, so it's a graph as well. It has a certain family of vertices and a certain family of edges. So the vertices of the dual graph will be the faces of the initial graph. So here the vertices of G star are these. And here G has an outer face, which is the infinite one. And G star will have a vertex here. So these are the vertices of G star. And the bonds or the edges of G star, so the dual bonds in E star, will connect vertices corresponding to faces sharing an edge of G. So the edges of G star will be something like that here. And here I made an example with a small graph, and that's making a lot of multiple edges on the outside. But that's the picture you get. You get one vertex for each face of the initial graph and one bond for each bond of the initial graph. So if E is a bond of the initial graph, it corresponds to a unique bond in E star, which I will write E star. So it's the dual bond of E. So this is just a combinatorial construction. If you take any planar graph, you will get a dual graph by doing this construction. So in the case of the square lattice, we will want to do the same construction. So we had a finite domain lambda in Z2, and that gave us some graph, some subgraph of Z2, which was a domain like this. So if this is lambda, if this is a graph in Z2, you can construct a dual graph, and it turns out that if you put one vertex for each face here, together with the dual bonds, what you get is a dual graph which looks like that. So the dual graph is also a piece of the square lattice, but somehow it's shifted by 1/2 in each direction. And if you want to do it properly in terms of graphs, you need also to put an outer vertex, and it's connected to each of the vertices here. But I will come back to that in a second. So the dual graph of lambda will be lambda star. And up to this outer vertex, you can see it as well as some subgraph of Z2. And if you want, you need to shift it by 1/2 to have an exact embedding in the plane. So this gives you a notion of the dual graph. And now we need to do some probability on that. So what do you want to do? The whole idea will be that we want to look at the connected components of a configuration omega. So we want a way to tell when all these components are finite or when there is an infinite one. So we want to have a way to describe the shape and the size of the components of omega. And the key idea will be, if there is a finite component or a small component in omega, that's because this is a set of open bonds, but it's surrounded by a set of closed bonds. And this fact of being surrounded by closed bonds, it turns out that there is a nice way to state it in terms of the dual graph. So if omega is a configuration, so it lives on lambda, which is a graph, what we'll do is we'll construct a dual configuration, omega star, which will be a configuration on lambda star, by saying that E star is open in the configuration omega star if and only if its corresponding bond in omega is closed. So this if and only if E is closed. And vice versa, if E is open, then E star is closed. So what it tells you is, if a component in omega is surrounded by closed bonds, it means that it's surrounded by dual bonds that are open for the dual configuration, and it means that it's surrounded by a circuit in the dual configuration. So maybe this will go better in the picture. I will do a picture here. So if this is lambda, and I will draw it in, I will do a very small example. If this is the configuration lambda, so it has just this component here in the middle, the dual configuration will have an open bond as soon as there is no bond in omega. So this will be in the dual configuration, and this will be just an isolated site in the dual configuration. And you see that this cluster here of omega is surrounded by a circuit in the dual configuration. So this is something that will be helpful because the topology of omega and omega star are related. And somehow you want to say that if omega has large components, then omega star has to live in the holes of omega, so it has to have small components. And if omega has only small components, it leaves a lot of room for omega star, so omega star will have huge components. So somehow the idea will be that omega is above the critical point if and only if omega star is below the critical point. So they cannot all belong to the same phase. If one is supercritical, the other has to be subcritical, and vice versa. So that's the idea, and to show that this is actually an equivalence, that will take us 2 hours and something. So that's essentially the goal of the whole proof, is to make this precise and to see what it tells us about the physics of the model. So if you want to do probability, the first thing to do is to look at omega star and see if we can describe its distribution in a simple way. So as warming up, let's look at the case of percolation. So percolation is the case Q equal to 1. What do you do for percolation? You say that each bond is open with probability P. So the probability that E is open is equal to P, and these events are independent across different bonds. So by the construction of the dual configuration, E star is open if and only if E is closed. So the probability that E star is open, this is the probability that E is closed, so it's 1 minus P. And these are independent as well, because the state of E star depends only on the state of E. So if omega is distributed according to percolation, so for Q equal to 1, then omega star has a configuration on the dual graph. This is distributed according to percolation with parameter 1 minus P and parameter Q. So there is a P star, which is the dual parameter here, and P star is 1 minus P. So in the case of percolation, the picture is very simple. If you look at the dual model, it's the same model with a different parameter P star. Now in the case of the random cluster model, it's a little bit more complicated. But what you know is that the weight of a configuration is proportional to y to the number of open bonds of omega times q to the number of connected components of omega. If you want to look at omega star and write its probability in terms of observables of omega star, well, this is the same as the probability of omega star, because there is an exact bijection. You just build omega star from omega. If you want to identify the distribution of omega star in terms of omega star, what you need to do is write these two terms, number of open bonds and number of closed bonds of omega, in terms of things describing omega star. And if you can do that, then you will identify the law of omega star. So this I leave as an exercise. So use Euler's formula to write the number of components in omega in terms of the number of components in omega star and the number of open bonds. So if you know Euler's formula, you just need to plug the parameters, and because it's written like y to something, it's not so difficult. It's just a little bit of bookkeeping, but it's a 3-line bookkeeping, so it's a nice exercise to do. But let's just one piece of it. The number of open bonds of omega is just the number of closed bonds of omega star, and that's the total number of bonds of omega star minus the number of bonds of omega star that are open. So O of omega star is n, the total number of edges, minus the number of open bonds of omega. So this tells you that in the formula for the probability of omega star, there will be somewhere y to the power minus O of omega star. So it tells you that there will be a dual parameter y star which somehow will look like 1 over y. To first approximation, if there was not this topological term, you would get exactly y to the minus O of omega star. And if you do that, you find exactly p star equals to 1 minus p. But if you take into account the number of connected components, what you end up with is a similar statement to what I wrote above here. So if omega is distributed according to the random cluster model with parameter p and q, then omega star is distributed according to a measure which turns out to be also a random cluster model, but it has parameter p star. It has the same parameter q, and p star is related to p by the formula which is p star over 1 minus p star. So this is y star, and this is equal to q. So that's the main relation. If you take a configuration according to the random cluster model, and you look at the dual configuration, this is again a realization of the random cluster model, but the parameter is different and is given by this simple relation. So here I'm cheating a little bit, and I will cheat all the way down to this blackboard, and then I will cheat a little bit less. Still a little bit, but not too much. So to come back to the main idea here, we want to say that if omega is above pc, then omega star is below pc, and vice versa. So we want to say that if p is larger than pc, then p star is below pc. But because there is this duality between p and p star, it's very natural to look for a fixed point. So look for the self-dual point characterized by p self-dual point star is equal to p self-dual. If you can find such a point, then you will notice that this relation exchanges the parameters above the p self-dual and the parameters below the self-dual point. So it's a very natural conjecture then that the critical point here will be exactly the same as the self-dual point. But now finding the self-dual point is not probability anymore. You just need to solve this, and you get that y self-dual is square root of q. So the p self-dual is just square root of q over 1 plus square root of q. So this is the self-dual point, and it tells you that if you take a random cluster model at the self-dual point, and you look at the dual configuration, it's a realization of the same random cluster model with the same parameter. So somehow it has to be critical. And the conjecture is that indeed pc should be equal to p self-dual. So far that's heuristic, and the goal of the, at least what follows in the course, is to change this word conjecture into a theorem. So that's the theorem. Way to go. That pc is indeed equal to the self-dual point on Z2 whenever q is at least equal to 1. So this is the main result that we would like to present, how to get from the heuristics telling you that it's a nice prediction that it should be the critical point to an actual proof that criticality occurs exactly at this parameter. Okay, I told you I cheated. Who saw me cheat? Who knows what the cheating is? Exactly. So the cheating is here. I didn't speak at all about boundary conditions. And in fact, Hugo cheated yesterday also about the boundary conditions. And as soon as you speak about the random cluster model, you need to be very careful about boundary conditions, because that's where all the difficulty is hiding. So why did I cheat? I cheated with not telling you what the boundary condition is. And if you look at P here, so if this is lambda, without boundary condition, so with free boundary condition, and if I look at the dual model, well, the dual model has a vertex outside the graph, which corresponds to the unbounded face, and is connected in the dual to all of these points by many edges. So this is a bit nasty, because the red graph, the dual graph of lambda, is not a subgraph of Z2. It has one bad vertex which is too big, which is surrounding the whole domain. What I can do instead is replace this vertex by many vertices all around the box, like this. So I put a whole layer of vertices here. But to have the same model, I will declare that they are always connected by open bonds. So I put open bonds all around. So it's the same. I had a big vertex. I split it across all the layer around the boundary. But I condition that they are connected. So it doesn't change anything in terms of the graph. It's the same as merging all these. What it changes is that this is now a subgraph of lambda, of Z2. It's a bit bigger, so it's not exactly the dual of lambda. It's something like size 1 more in each direction. And connecting these vertices on the boundary, it's exactly looking at the wired boundary condition. So what you get is that if omega is distributed according to PQ with free boundary conditions in lambda, then omega star is distributed like a wired configuration with parameter P star, Q, in a box lambda which is a little bit bigger. I will still want to call it lambda star, but lambda star is not the dual in terms of graphs, it's just a box which is a little bit bigger. So now there is no cheating, this is an exact statement. But it tells you that there will be a problem, because at the critical point, we don't have a fixed point yet. We don't know that at the critical point, this is equal to this, because they still have different boundary conditions. So we'll need to be very careful about that. And actually, at the critical point, we expect that these measures are actually different in the scaling limit, in the thermodynamical limit. So this is what you have to keep in mind, but it's still true that morally there is this duality between P and P star, and the heuristics should still work. So this is what I wanted to say about duality. It tells you that there is this relation between P and P star, and that we kind of expect any feature of the model on the left to translate into a feature of the model on the right. And so we want to show that P is equal to P, that the critical point is equal to the self-dual point. Maybe I want to be... Okay, I will denounce Hugo again. I will tell you where he cheated yesterday. Because now if we want to prove something like that, we need to define PC properly. And to define PC properly, or you cannot cheat, because if you cheat, you don't have a nice definition and you cannot prove anything about it. So recall what Hugo did. What he did was to construct a measure in the whole lattice Z2 as a limit of measures in small boxes. So what he did was to construct P0, PQ in Z2 as the limit, increasing limit, of P0, PQ in an n by n box. And he defined P1 in PQ Z2 as the decreasing limit of P1, PQ in finite boxes. So this is perfectly okay. Here you have zero boundary conditions which goes further and further away, so it has fewer and fewer effects on the local behavior of the model. So you get an increasing limit, and because it's increasing, it converges. And P1 is the same story. It decreases because the positive effect is further and further away. So this is well defined. And that's okay. And then what he argued was that there's monotonicity in P for fixed Q. And this is given by a coupling between configurations. So what you can look at is theta of P, which is the probability that 0 is connected to infinity. And then theta of P is an increasing function, is a non-decreasing function. So it's 0 up to a critical point, and it's positive afterwards. So this gives you a critical point as a threshold between parameters where theta is 0 and parameters where theta is positive. So this was the story for percolation, and if you want to do it for the random cluster model, well, as I told you, you cannot cheat, so you need to speak about the boundary condition. So in fact, it doesn't make sense yet to write P here. You need to keep in mind that there are boundary conditions. So I'm hiding Q. Q is fixed for now, bigger than 1. But I still have these two functions, theta 0 of P and theta 1 of P, which are the probabilities that 0 is connected to infinity for the measure P0 and for the measure P1. And because of the monotonicity of the model and because of the way it depends on the boundary conditions, while theta 0 is less than theta 1. So you know that if you percolate for free boundary conditions, you also percolate for wired boundary conditions. And then a priori, you can define two critical points. You can define PC0, which is the inf of P such that theta 0 of P is positive. And you can define PC1, which is the inf of P such that theta 1 is positive. And if you want to even state the theorem that PC is equal to something, well, you need to argue that there is a unique critical point. So you need to show that PC0 is equal to PC1. And all you have for now is that because theta 1 is bigger than theta 0, it will become supercritical not later than that. So what you have is that PC0 is at least equal to PC1. But what could happen is that there would be difference. PC0 would be strictly bigger, and in between, the P0 measure would be subcritical, but the P1 measure would be supercritical. So this is not actually a big problem in the case we are looking at, because what you can do, and I will not do it, but I will tell you where to look. So if you look at Grimet's book on the random cluster model, you will see the whole proof of the statement here I'm writing. So the theorem is the following. For every Q at least equal to 1, there exists a set dQ which is at most countable so a very small set such that whenever P is not in dQ, P0P is equal to P1P. So there cannot be disagreement between P0 and P1 for many parameters. They have to match on the dense set.
P is not in dQ.
Is not in dQ, yeah. So whenever you are not in a countable set, P0 is equal to P1. And what it tells you is that it's not possible that P0 is strictly bigger than PC1, because in between, you would have some point which is not in dQ. And for this point, you would get a contradiction, because if you are strictly between, then theta 1 would be strictly positive, while theta 0 is 0. but they have to be equal because the measures are the same. So this tells you that PC is well defined. So this implies that PC0 is equal to PC1. Okay, so now we have a clear definition of the self-dual point, and this is combinatorics. We have a clear definition of PC, which is coming from probability, and what we want to show is that they are equal. So how do you show that two numbers are equal? You show that they are ordered in the two directions at the same time. So what I will do now is to show you one inequality. So what I will show is something called, maybe I should restart here. What I will show is the easier bound. And essentially, I will tell you that the self-dual point cannot be in the supercritical regime. So first inequality, which I want to write like this, P self-dual is not strictly larger than PC. So it tells you that PC is at least equal to P self-dual. But since it's a proof by contradiction, I will write it like that. And this is known as Zhang's argument. So for those of you who have followed the course on percolation, question?
Yeah, I'm just curious if you know that PC is in DQ or not.
Okay, that's a very good question. And the answer is we don't quite know, but there is a prediction. So that PC is in DQ, that's called first order phase transition in physics. And the conjecture is that PC is in DQ if and only if Q is larger than 4. So for large Q, we expect first order phase transition, and for small q, we expect second order, so we expect that P0 is always equal to P1. And this, we know how to show that it is in DQ if Q is large enough, bigger than 25 point something. And Hugo is working on proving that it is not in DQ for Q less than 4. And I think he will maybe mention that on Friday. Where is Hugo? Will you mention that on Friday? Okay. But he knows how to do it. In between 4 and 26, we don't know.
If the measures are different, that doesn't imply that the theta are different.
No. But there is actually a
First order phase.
yeah, well, yes, somehow, but yeah, we expect second order if Q is less than 4 and first order if Q is more than 4. And the way you characterize the difference of the measures is that actually one is supercritical and the other one is subcritical. So it turns out that the characterizations are the same. It's not obvious from the definition, but it comes from the proof.
So DQ is not empty.
Sorry?
DQ is not empty.
DQ is not empty if Q is large enough. I'm not writing all the conjectures about DQ, but we expect that actually DQ is just the critical points for large Q and nothing if Q is less than 4. But I don't want to go in this direction because that would take a lot of time and I would have to speak about free energy and these kind of things. So there are a few things known about DQ, but we won't use them that much. All we need to know is that PC is well defined. Okay, so now I'm going on with the proof. Maybe I will have time to do this and a little bit more. So here's the argument. Assume that P self-dual is bigger than PC. So assume that at the self-dual point, you have that theta of P self-dual is strictly positive. And actually, I'm assuming this. I'm assuming that theta 0 is positive. But that's the same because we know that theta 0 is positive whenever theta 1 is positive by this argument. So I'm assuming that theta 0 of P self-dual is positive. And I want to get to a contradiction. So how do I do that? Well, the first fact, so fact 1, is so whenever theta of any boundary condition is positive, actually there is a unique infinite component. So this is something that comes from the ergodic theorem, essentially. First, you show that the number of infinite components has an almost sure value. It's not a random number. And then you show that it cannot be a finite number not equal to 1, because if you have two components, you can always merge them by changing the state of finitely many edges. And then it cannot be infinite, because if it were infinite, there would not be enough space to fit them in the big box. So I'm referring you to Grimet for that. But it's a very general argument that works for any model with enough regularity on a lattice. So this is almost surely with probability 1. So if theta is 0, there is no infinite component, and if theta is positive, there is a unique infinite component. Okay, so that's the fact we want to contradict. What we'll do is, assuming that theta is positive, we'll prove that with positive probability there are actually two infinite components, and that will contradict this fact. So how do you do that? So fact number 2. Fact number 2 is that if you look at P0 at the self-dual point on Z2, you can look at the dual measure. If you have a configuration in Z2, you can look at the dual configuration in the dual of Z2, which is Z2 shifted. The boundary conditions, they evaporate to infinity, and they are changed into this 0 and 1 here. So if you look at the dual measure of this, well, this is the same as P self-dual Q in Z2 with one boundary condition. So this is P1, P self-dual, Q on Z2. So this comes from the duality I introduced before. It's just going to the limits in this. And what it tells you is that the dual model will be at the self-dual point. But it has one boundary condition, which is bigger than 0. And we know that, so besides, we know that theta 1 of P self-dual, this is at least equal to theta 0, so it's also positive. So if we start with the assumption that P self-dual is supercritical, we have omega, which is supercritical, so it has an infinite component. And if you look at the dual configuration, it's distributed according to P1, which has positive theta, so it also has a unique infinite component. So this assumption, P self-dual bigger than Pc, implies that there is coexistence of infinite components for the model and for the dual model at the same time in the same lattice. So what we need to argue is that there is not enough room in Z2 to fit an infinite component and a dual infinite component. So this is where the argument lies. So it's a very graphical argument. It's a very smart argument, actually. And it goes like this. So I will skip some of the details, but I will focus on one particular feature because that's something we will use again later. So assume that theta self-dual is bigger than Pc. You know that there is a unique infinite component somewhere on the lattice. Now take lambda n, which is a large box on the lattice around 0. Well, the existence of an infinite component is given to you. It's measurable in the process. So you can approximate it by a finite volume event. So you know that if n is large enough, you will meet this infinite component with high probability. So with probability 1 minus epsilon, you will meet the infinite component with the box. So take a box large enough that you will discover the infinite component. So this box is connected to infinity by an infinite component of open edges. Now, you don't know where this infinite component lands on the box. The second step is to say that if the box meets the infinite component with high probability, then actually the right side of the box will hit the infinite component, and that the right side will be connected to infinity outside the box. So somehow, if you meet the infinite component, you can locate from which side you are connected to infinity and say that this probability is not 1/4, it's also close to 1. So this is something very crucial in the proof that will follow. And it's known as the square root trick. And it's actually an easy consequence of the FKG inequality. So here it goes. So the lemma is called the square root trick. So if you want to remember one thing from the course of today, if you have to choose one thing, choose this lemma. Don't choose the story of the random cluster model, but remember this, because that will be useful in many other cases. So the idea is, if A is a union of AN, and all the events are increasing, and the AN of the AI, I from 1 to n. So if you can split an increasing event into pieces which are also increasing, and if the AI have the same probability, so if you can split an event into increasing events of the same probability, and if the probability of A is large, then each of the pieces has to have a large probability. So I will tell you the proof before I state the lemma, because it's more natural that way. So look at the complement. So the complement of A is the intersection of the complements of AI. And now we are speaking about the random cluster model. So this is stated for the random cluster model. So the AI complement, they are decreasing events. And because of the FKG inequality that Hugo stated yesterday, decreasing events are also positively correlated. It's the same argument as for increasing events. So this probability that A complement is the probability of the intersection of the complements of the AIs. These are decreasing events, and you look at the intersection, so this is bigger than the product of probabilities of the AI complements. So this is from the FKG inequality. So once you have this is the product of 1 minus P of AI, and they have the same probability. So this is 1 minus P of A1 to the power n. And this, on the other hand, is 1 minus P of A. So now what you get is that P of A is bounded above by 1 minus P of AI to the power n. So this is the statement of FKG, reshuffled a little bit. And now remember, the statement was if A has large probability, then the AI have large probability. So you want to turn this into a lower bound on P of AI. And well, it's obvious what to do. You shift the thing together and you write the formula backwards. And what you get is that P of AI is at least equal to 1 minus P of A to the power 1 over n. So this is the statement of the square root trick. And it comes from the name where n equal to 2, that you can get a lower bound in terms of square root of the error here. But it tells you that if P of A is close to 1, then this is small, so this is also close to 1. Okay, if you want to apply this here, well, A will be the events that the box is connected to infinity, and you will split that into the union of 4 events, which are this side is connected to infinity outside the box, this side, and that side. And these 4 events, they have the same probability because the model is completely symmetric with the reflections here. So if you are connected to infinity, this side is connected to infinity. So you know that this occurs with high probability. Now, this occurs with high probability as well because it's the same event. And the two occur at the same time with high probability by the FKG inequality. So this is an event of large probability. Now, remember the dual model is distributed according to P self-dual with a 1 here. So every probability for the dual is larger than the probability for the initial model. So what you get is that the dual is connected to infinity. So this side is connected to infinity by a dual path with very high probability. And the bottom side, which maybe you don't see, but it's also connected to infinity by a dual path. So all these events have probability close to 1. So by a union bound, what you get is that their intersection here also has probability large, very close to 1. And now, on this event, well, there are two things that can occur. Either this and this are connected inside the box. And if they are connected inside the box, then you know that this component and this component are two infinite components in the initial lattice. And that's impossible because you have uniqueness of the infinite component. So this is impossible. And if this doesn't occur, then somehow these are connected inside the box. And so you have two components in the dual configuration. So either way you get a contradiction because you know that almost surely there can be only one infinite component in each of the phases. So just by FKG inequalities plus the assumption that you percolate at the self-dual point, you get a contradiction because you violate uniqueness of the infinite component. So that was kind of an easy proof once you know how it starts. And it tells you that there's a contradiction if you assume that P self-dual is bigger than PC. So from this we get that P self-dual is bounded above by PC. And that gives us one bound on PC. PC is at least equal to the self-dual point. Now the question is, I have 7 minutes. So in 7 minutes I will tell you the plan for tomorrow's lecture. And the plan for tomorrow's lecture is to prove the converse inequality, of course. So what remains to do so just a word about this. This was known before. This inequality was known before, and Zhang's argument initially it was stated for percolation. But what I say is exactly the same proof as for percolation. Only for percolation you don't need to distinguish the two boundary components, but the argument is exactly the same. So what remains is what is new is the other inequality. So you want to show that PC is at most equal to P self-dual, and for that we'll show that for any epsilon positive, P self-dual plus epsilon is supercritical. So what we want to show is that for any epsilon positive, theta 1 of P self-dual plus epsilon is strictly positive. So this is what we have to show. Maybe the self-dual point is not super critical in the sense that it doesn't percolate, but as soon as you enhance it a little bit, it becomes super critical. If you can show that, then you get this bound and you get the equality between PC and P self-dual. So the plan is this. Essentially, there are two steps in the proof. So step 1 is to show that P self-dual is almost supercritical. Is almost supercritical. And by that, what I mean is, at the self-dual point, you already see something which is macroscopic. Maybe you don't see an infinite component, but you see large components. And a precise statement would be that P1 at P self-dual of something like that, take a box and you look for an open cluster crossing the box. So something of size n. This has probability bounded below uniformly in n, which is the size of the box. So alpha n. So again, for those who know percolation, this is similar to the Russo-Simon-Welch theory for percolation. And this is telling you that P self-dual is not deep in the subcritical region. You expect that if you are subcritical, the clusters are very small. And if you look at the biggest cluster in the box of size n, it should be of size logarithm of n. So this tells you that P self-dual is not very subcritical. And then the step 2 will be to show that if you have a bound like this, which is positive, so this is positive, if this is positive for P self-dual and you increase P a little bit, then you will make this probability very close to 1. So P1, P self-dual plus epsilon of the same thing will be close to 1. And step 3 will be, once you have that this is close to 1, show that theta of P self-dual plus epsilon is actually positive. So show that if you can cross large boxes with probability close to 1, actually you can build an infinite cluster. So step 3 will be very short actually, but step 1 and step 2 will be the main meat of the proof. So tomorrow I'll do step 1 and maybe step 2 if I have time. And if there is no time, then this is for next course and this will be for Friday. So we'll see how fast it goes, but we'll see that tomorrow. No, Thursday. Okay, I better stop here. So thanks.